When we start moving terms around inside an infinite series or applying algebraic transformations to them, we often uncover behaviors that are entirely invisible at first glance. Standard evaluation tools, like the root and ratio tests, do an excellent job handling series where the terms converge absolutely. But if a series only converges conditionally, where the positive and negative terms cancel each other out in a very specific order, those tests break down entirely. To evaluate these trickier, conditionally convergent series, we need a specialized discrete tool. That tool is summation by parts, and it forms the mathematical backbone for advanced topics like Fourier analysis. You might recognize the name. It's the exact discrete equivalent of integration by parts from calculus. Just as we use integration by parts to break down the product of continuous functions, we use summation by parts to handle the product of a discrete sum. Dealing with discrete, oscillating mathematical problems requires precise, discrete tools. By adapting this calculus concept, we can isolate the specific structural stability hidden inside a volatile series. Let's look at Walter Rudin's definition. Here, in Theorem 3.41, we start with two sequences, a sub n and b sub n. Notice how the capital A sub n is explicitly defined as the partial sum of the sequence a sub k. If we move down into the proof, we see the first crucial step. The individual term little a sub n is substituted out. It's instead represented as the difference between two partial sums, capital A sub n minus capital A sub n minus 1. This substitution allows us to shift the mathematical weight of the expression. By factoring capital A out, the heavy lifting moves away from little a, and we naturally force the generation of a new difference term, as seen in the final expression on the right. This graph illustrates why that shift matters. Theorem 3.42 establishes the two primary conditions required for this sum to converge. First, the partial sums of capital A sub n must form a bounded sequence, trapped between these upper and lower limits. Second, the terms of sequence b sub n must steadily shrink to 0. We can immediately apply this to prove the alternating series test, or Theorem 3.43. If we assign little a sub n to handle the alternating sign, oscillating precisely between 1 and -1, we can pair it with a b sub n sequence that represents a decaying magnitude. The steady decay of b dampens the oscillation of a. Summation by parts acts as a balancing mechanism. It allows us to safely manage a stubbornly oscillating sequence by linking it to a predictably decaying one, guaranteeing the overall product converges. Let's extend this logic to power series. Theorem 3.44 tests the convergence of a series containing a complex variable z, specifically looking at the boundary circle where the absolute value of z is exactly equal to 1. Think about how we just set up our balancing mechanism. If we define our decaying sequence b sub n as the coefficients c sub n and our alternating sequence a sub n as z to the power of n, how do we use the geometric series formula to find the bounded partial sum, capital A sub n? We use a geometric series substitution. Evaluating the sum of z to the power of k yields a fraction. Taking the absolute value of that result shows that our partial sum, capital A sub n, is strictly bounded by 2 over the absolute value of 1 minus c, provided z does not equal 1. Finding these strict bounds leads directly into Theorem 3.45 and the definition of absolute convergence. If the sum of the absolute values of a series converges, then the standard version of the series is absolutely guaranteed to converge as well. The proof for this relies on the Cauchy criterion and the triangle inequality. As shown in the top inequality here, the absolute value of the entire sum can never exceed the sum of the individual absolute values. If the larger absolute sum meets the criteria for convergence, the smaller standard sum must comply. But look at remark 3.46. Not all convergent series meet this standard. The alternating harmonic series, -1 to the n over n, is a classic example of a series that converges non-absolutely. Its absolute form diverges to infinity, even though its alternating form settles on a finite number. Absolute convergence provides unshakable structural stability. Conditional convergence, by contrast, is a highly delicate state. It relies entirely on the precise cancellation of terms, requiring exact mathematical scalpels, like summation by parts, to prove the structure won't collapse. To recap, summation by parts is the tool for transforming conditionally convergent series into solvable equations. It works by separating the components, isolating bounded oscillation in capital A sub n from the steady decay in b sub n. We contrast that careful balancing act with absolute convergence. By taking the sum of the absolute values, we test for the strongest, most resilient form of convergence, one that is immune to issues caused by rearranging the sequence. Mastering these specific tests allow us to look past the top-level numbers and see the hidden architecture governing an infinite series. These exact definitions of stability form the necessary foundation for all higher mathematical analysis. If you want to continue building that foundation, subscribe to the channel. We'll be breaking down more essential theorems and proofs from advanced texts like Rudin, step by step.